Okay, one more time. If you have two tar molecules, no, they will not. But it doesn't matter if they can interact here, they can interact here, 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 here. You could turn it around and you can do everything. As long as you have long chains of carbohydrates, hydrophobic interaction is an attraction force. It's not a bond. It's an they will aggregate. They will not bond. With a nucleotide which will be surrounded by water molecules, these little Mickey Mouses. In order for this nucleotide to make a covalent bond with another nucleotide, you will have to align perfectly in a 3D structure. That is not as likely as two long chains hydrocarbons making a hydrophobic interaction. There will be a time difference between how long it takes for a nucleotide to find another nucleotide and align in a perfect alignment to create a new covalent bond. These two just need to get very close together, and they will make an interaction, regardless how they how they pose themselves in this 3D environment. So there's definitely a time scale difference between hydrophobic interactions and nucleotides making covalent bonds. Basic chemistry, pal. According to the D sugars, well, in your video you said that I was only talking about amino acids. I never addressed the nucleotides. And then, yeah, okay, you addressed the sugars, but you didn't address the nucleotides. But you just said I didn't address. You only said I was talking about amino acids, so that's where you're wrong. I will just read you the summary of this article. In summary, it seems conceivable that amino acid catalyzed formation of hexoses presented herein may be an example of the theoretical basis for the evolution of homochirality of sugars, that is, all sugars, from a low optical purity of the catalysts. The intrinsic ability of amino acids catalyze the asymmetric formation of carbohydrates, that is, all carbohydrates, which enzymes have mediated for millions of years, suggest a plausible, it isn't impossible, it's just plausible, ancient catalytic process that perhaps still occurs both on Earth and elsewhere in the universe. Further genetic and molecular modeling studies are ongoing. In organic chemistry, there are millions or perhaps billions of chemical reactions. So how can anyone study chemistry? Well, the great thing about chemistry is that you only have to know about 20 or so different types of chemical reactions. They are all the same. There's large family groups of chemical reactions. Regardless of the substituents on a particular molecule, they will always follow the exact same laws of chemistry. That is, if you have a ketone, almost all ketone reactions are exactly the same. The only difference is the timetable, how the kinetic energy for the reaction differs if you have to have a catalyst or not. If you have a hydroxy groups, regardless of what other molecules the hydroxy group sits on, they will undergo the exact same chemical reactions as other hydroxyl groups on other molecules. So we only have to demonstrate how to make these sugars want to have a plausible chemical reaction. Basic chemistry, pal. Yeah, okay, you're a university student and always refer to Wikipedia. What kind of a fucktard university do you go to? You can't find the article online because you have to pay for it? Well, here's Google. Type in plausible origins of chirality carbohydrates. Search. Let's see, the first hit is plausible origins of homochirality in the amino acid catalyzed. Let's click there. And what do we have here? Free access, PDF, and ooh, it's the entire article for free. Oh my, that took me 2 seconds. Yeah, that's Google, pal. And that's the Wikipedia definition of a scientist. Yeah, Wikipedia. Everything you read on Wikipedia is true. Here's my definition of what a scientist is. Someone who uses the scientific method. You don't use the scientific method in mathematics, nor do you do it in philosophy. Wikipedia rules. I found it on Wikipedia. It must be true.